Temperature conversions. Converting from Celsius to Fahrenheit is simple. 1.8 is the number to remember. Use the formula degrees Celsius times 1.8 plus 32 equals Fahrenheit. For example, if we wanted to find out what 30 degrees Celsius is in Fahrenheit, we would simply plug in 30 degrees into the formula. 30 times 1.8 plus 32 equals 86 degrees Fahrenheit. Fahrenheit to Celsius. Let's look at another example, but this time converting Fahrenheit to Celsius. 1.8 is still the number to remember. The formula is Fahrenheit minus 32 divided by 1.8 equals Celsius. What is 50 degrees Fahrenheit in Celsius? 50 minus 32 divided by 1.8 equals 10 degrees Celsius. Let's work through an example. Click the next button or on each tab to see how to calculate the correct answer. Temperature difference is represented by TD or delta T. Temperature difference is the change in temperature between the return duct and the supply duct. To figure out temperature difference, subtract the temperature of the return air from the temperature of the supply vents. The ideal temperature difference between the supply and return air is usually between 16 degrees and 22 degrees Fahrenheit. Do not confuse temperature difference with design temperature difference. Design temperature difference, DTD, is the difference between inside design temperature and outside design temperature. Let's work through a different example. Click the next button or on each tab to see how to calculate the correct answer. Thermal resistance. R value and U value. Both R and U values measure a material's thermal resistance. Thermal resistance is how easily heat flows through a material. R values must be converted to U values in order to be used in formulas. U values represent the amount of BTU per hour transferred through 1 square foot of material per degree temperature difference across the material. BTU, or British Thermal Unit, will be covered next. R value versus U value. R value. The R value is a measure of resistance to heat transfer through a given thickness of material. Higher numbers indicate better insulation performance. Reciprocal of U value. R value equals 1 divided by U value. R values are numbers assigned to a product. May be added up proportionally. U value. U value is a measure of how much heat is lost through a given thickness of a particular material. Lower numbers indicate better insulation performance. Reciprocal of R value. U value equals 1 divided by R value. More accurate because U values account for convection and radiation heat losses. Add up R values first, then convert it to a U value. R value and U value formulas. The formulas for R and U values are reciprocals of each other. R value equals 1 over U value. U value equals 1 over R value. Memorize these formulas. Let's work through an example. Click the next button or on each tab to see how to solve in the correct answer. A wall has an R12 rating. The wall insulation has a R18 rating. What's the overall R value? R values may be added up proportionally. 12 plus 18 equals 30. The wall has an overall R value of 30. Let's work through an example. Click the next button or on each tab to see how to solve in the correct answer. Converting R value to U value. If there's R30 insulation in an attic, what is the insulation U value? To solve, use the U value reciprocal formula. U value equals 1 divided by R value. The answer should be 0.033 repeating. Let's work through another example. Click the next button or on each tab to see how to solve in the correct answer. Converting U value to R value. If insulation has a U value of 0.25, what is the insulation's R value? To solve, use the R value reciprocal formula. R value equals 1 divided by U value. 1 divided by 0.25 makes the R value equal 4. Let's work through another example. Click the next button or on each tab to see how to solve in the correct answer. BTU stands for British Thermal Unit. BTU is a unit of measurement. You should memorize where BTU comes from, as it's a common test question. It's the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. You will see BTU written out with all letters capitalized or lowercase. BTUH means BTUs per hour. BTUs per hour is used as a benchmark to express capacity. A ton of refrigeration, TR, or refrigeration ton, RT, is a unit of power. 1 ton of refrigeration is the amount of heat needed to melt 2,000 pounds of ice in 24 hours at 0 degrees Celsius. Rated in BTUs or refrigeration tons. 1 ton equals 12,000 BTUs per hour, or 3.517 kilowatts. You should memorize 1 ton of refrigeration equals 12,000 BTU per hour. Let's work through more examples. Click the next button or on each tab to see how to solve in the correct answer. If a 1-ton air conditioning unit produces 12,000 BTUs per hour, how many BTUs does a 3-ton air conditioning unit produce per day at 100% efficiency? To solve, first multiply 3 tons by the 12,000 BTUH. 3 times 12,000 equals 36,000 BTUH. Next, multiply by 24 hours because the question asks per day. 36,000 BTUH times 24 equals 864,000 BTU per 24 hours, or 864,000 BTU per day. Let's work through another example. Click the next button or on each tab to see how to solve in the correct answer. FPM and CFM. FPM equals feet per minute. CFM equals cubic feet per minute. In other words, FPM refers to the air speed, or how fast the air moves. CFM refers to the air flow, or how much air is moved. Cubic feet per minute equals feet per minute times area, in feet. Cubic feet per minute is used frequently in HVAC work to measure airflow. Another formula for CFM is volume times air changes per hour divided by 60 minutes. Calculating CFM using the formula. A 1,600 square foot house with 8-foot ceilings requires 0.35 air changes per hour. What is the airflow rate? Answer. First, multiply the square footage by the ceiling height. 1,600 times 8 equals 12,800. Next, multiply by the number of air changes per hour. 12,800 times 0.35 equals 4,480. The question does not specify the time unit of measurement of the airflow rate, but using CFM is more typical than per hour. Keep going to find the cubic feet per minute. Divide the number by 60 minutes. 4,480 divided by 60 equals 74.67 cubic feet per minute. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Air changes per hour, ACH. The formula for air changes per hour is cubic feet per minute times 60 divided by volume. This formula is basically how many cubic feet of air an HVAC unit can provide every hour divided by the volume of the room. Note that CFM is expressed volume of air per minute, while ACH is expressed in hours. How frequently should air be exchanged? The recommended exchange rates for residential homes is 0.35 to 1 air changes per hour. The recommended exchange rates for retail stores is 2 to 3 air changes per hour. The recommended exchange rates for schools is 5 to 6 air changes per hour. The recommended exchange rates for restaurants is 6 to 8 air changes per hour. The American Society of Heating, Refrigerating, and Air Conditioning Engineers recommends that homes receive 0.35 air changes per hour, but not less than 15 cubic feet of air per minute, CFM, per person, as the minimum ventilation rates in residential buildings. As you can see from the table, recommended ventilation rates vary from 0.35 to 8 air changes per hour. Let's work through an example question. There is a unit with 250 CFM airflow in a 440 square foot room with the 8-foot high ceiling. How many air exchanges per hour should the unit make? Remember, the air changes per hour formula is CFM times 60 divided by volume. Step 1. Convert from cubic feet per minute to cubic feet per hour. 250 CFM is cubic feet per minute. In 1 hour, 60 minutes, we get 60 times 250 equals 15,000 cubic feet per hour. Step 2. Find the volume of the room. 440 feet squared times 8 feet equals 3,520 cubic feet. Step 3. Use the formula ACH equals CFM divided by volume. 15,000 divided by 3,520 equals 4.26. Such unit can change all the air in room 4.26 times per hour. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Inches of water column is another unit of measurement. It is equal to the amount of force it takes to raise the column of water by 1 inch in a water manometer. Low pressures, less than 1 PSI, are measured in inches of water column. 1 PSI is equal to 27.71 inches of water column. Used for measuring static pressure, an instrument called a pilot tube measures velocity pressure in inches of water column. Pilot tube instrument reads the velocity pressure in inches of water column. Velocity, V, means the distance traveled over a certain time period. Air velocity is usually expressed in feet per minute. By multiplying air velocity by the cross-section area of a duct, you can determine the air volume flowing past a point per unit of time. We will be using minutes as the standard because volume flow is measured in cubic feet per minute, CFM. CFM is a measure of air velocity. Velocity is different than speed. Speed equals distance over time and conveys how fast something is moving. Velocity equals change in distance over change in time. So velocity is the rate and direction which an object changes position. Velocity and velocity pressure. Velocity is measured in feet per minute, while velocity pressure is measured in inches water column. Positive pressure pushes air. Negative pressure draws air. Velocity pressure, also called pressure velocity or PV, is expressed in feet per minute. The formula for velocity is 4005 multiplied by the square root of the velocity pressure. The square root of the PV reading is multiplied by 4005, a number carefully derived by the famous 18th century Swiss mathematician Daniel Bernoulli. 4005 is a constant used in calculating a velocity pressure in relation to inches water gauge pressure and velocity when expressed as feet per minute. The density of air, 0.075 pounds divided by feet to the third, is built into the formula. Let's practice. What is the airflow velocity for a velocity pressure reading of 0.75 inches water column? Use the formula to find the answer. Flow velocity equals 4005 times the square root of the velocity pressure. Therefore, 4005 times the square root of 0.75. The square root of 0.75 is 0.866. 4005 times 0.866 equals 3,468. The flow velocity is 3,468 feet per minute. Let's work through another example. Click the Next button or on each tab to see how to solve in the correct. Let's work through another example. Air is moving through a duct at 1,640 feet per minute. What is the velocity pressure? 1,640 FPM divided by the 4005 constant. 1,640 divided by 4005 equals 0.409. Then square the result. The answer is given in inches of water column. 0.409 squared equals 0.168 inches of water column. Let's work through another example. Click the Next button or on each tab to see how to solve in the correct answer. If the average velocity in a 10-inch diameter duct section measures 1,500 FPM, what is the volume flow rate at that point? First, find the area of the duct. The area of a circle is pi r squared. Divide the diameter by 2 to get the radius. Convert the radius from inches to feet. The radius is 0.417 feet. Pi r squared makes the area 0.55 square feet. Plug the numbers into the continuity equation formula to find the answer, which is 819 cubic feet per minute. Calculating CFM, airflow, or volume. The formula for CFM is the duct area times FPM. The CFM formula is used frequently. Memorize the CFM formula. What is the CFM for a 1.07 feet squared duct with a velocity pressure of 0.45-inch water column? Use the CFM formula and the FPM formula to solve. CFM equals duct area times FPM. Plug in the FPM formula. CFM equals duct area times 4005 times the square root of delta P. Next, plug in the given numbers and solve in the order of operations. CFM equals duct area times 4005 times the square root of 0.45. CFM equals duct area times 4005 times 0.67. CFM equals 1.07 times 2,683. CFM equals 2,871. Volume formulas. CFM equals area times FPM. Duct dimensions are often given in inches, not feet. When we use inch units of measurements, we need to expand the formula to CFM equals duct cross-sectional area 1 times duct cross-sectional area 2 times FPM divided by 144. If the duct dimensions in inches and feet per minute, FPM, are given in the question, you need to convert the duct dimensions from inches into feet. Because the answer will be in cubic feet per minute, this is where the 144 comes from. Pay attention to the duct dimensions. If they're given in feet, you'll need to convert them to inches first for this formula to work. Remember, ducts come in round, square, and rectangular dimensions. Airflow formula. We've learned to calculate airflow in a duct by measuring the airflow velocity in feet per minute, FPM, and multiplying by the duct cross-sectional area in square feet. CFM equals D1 times D2 times FPM divided by 144. Let's work through another example. What is the airflow of a 10-inch by 6-inch duct with an airspeed of 2,000 feet per minute? Find the area using the formula. Remember to divide by 144 to get the answer in CFM. 10 times 6 times 2,000 equals 120,000. 120,000 divided by 144 equals 833.3 CFM. Let's work through another example. Click the next button or on each tab to see how to solve. You have 120,000 BTU-H output furnace, and you need to supply air at 120 degrees Fahrenheit. The room temperature is 73 degrees Fahrenheit. What is the CFM required? First, find the temperature rise, delta T. 120 degrees Fahrenheit minus 73 degrees Fahrenheit equals 47 degrees Fahrenheit. Next, use the formula. CFM equals BTU-H divided by 1.1 times temperature rise. CFM equals 120,000 divided by 1.1 times 47 equals 2,321 CFM. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Duct airflow calculations. What is the air velocity? First, find the area. 8 inches times 10 inches equals 80 square inches. Next, convert square inches to square feet. 1 square foot is 144 square inches. 80 square inches divided by 144 equals 0.56 square feet. Air velocity, FPM, equals CFM divided by duct area in square feet. FPM equals 600 divided by 0.56. FPM equals 1071.43 FPM. Multiple diverging flow. The total volume flow rate, CFM, at any point is the sum of all the downstream volume flow rates. Equivalent length, or EL, is the value of the comparison length of this fitting to an equivalent length of straight pipe or duct. It accounts for static pressure lost in a fitting that would be comparable to a length of straight duct. The total effective length, TEL, is the sum of all fitting equivalent lengths and the measured straight duct length. For example, the total effective length of a 90-degree square to rectangular elbow is the equivalent length of 35 feet of straight duct. Duct design methods. There are 3 acceptable duct design methods. They include the equal friction method, the static regain method, and the constant velocity method. The equal friction method is easier to use, but it does not account for varying lengths. You must use friction loss rates for 100 feet of duct. The equal friction method presumes that friction in ductwork can be balanced to allow uniform friction loss through all branches. The static regain method is typically used on larger systems and is more efficiently balanced. The static regain method is only used for supply air. The constant velocity method is not commonly used. The equal friction method. But first, what is friction rate? Friction rate is a value that calculates the design friction rate from the 2 variables, available static pressure, ASP, and total effective length, TEL. The available static pressure is what's left when you take the total external static pressure and subtract the pressure drops for all the things that are not ducts and fittings. That's how much of a push you have left to move the air through the ducts. The total effective length is the sum of the duct lengths and the fitting equivalent lengths. Here's how to take those numbers and calculate the friction rate. Let's say the available static pressure is 0.31 inches of water column, and total effective length is 424 feet. What is the friction rate? 0.31 divided by 424 equals 0.00073 inches of water column per foot. However, friction rate is usually given not as the pressure drop per foot, but instead as the pressure drop per 100 feet. This is a friction loss chart for round ducts. Click Resources at the top right to enlarge the image. Duct diameter lines are diagonal going up from left to right. Velocity in feet per minute is indicated by the lines running down diagonally from left to right. Friction loss is listed on the left y-axis. Air quantity in cubic feet per minute is listed on the x-axis. What is the pressure loss per 100 feet in a 12-inch diameter duct delivering 1,000 CFM? Try to solve this one on your own. The answer is 0.2 inches per 100 feet. The equal friction method process. First, find effective length, EL, of the longest run. Second, establish allowed static pressure loss per 100 feet. Third, size the duct. Then, repeat for each branch. The velocity must be higher in each upstream duct section. Let's look at an effective length example. Effective length. Before we can find the effective length of the longest run, what is the longest run in actual dimensions? 30 plus 12 plus 8 plus 6 equals 56 feet. The longest run is 56 feet. If 56 feet is the longest actual run, what is the longest run's effective length? Given straight fitting equivalent length is 5 feet, elbow equivalent length is 10 feet, AHU connection 50 feet. First, label the duct sections. Given straight fitting equivalent length is 5 feet, elbow equivalent length is 10 feet, AHU connection 50 feet. Then, solve for each section. Section A equivalent length is 10 feet because it has one elbow equivalent length 10 feet. Section B equivalent length is 5 feet because it has one straight fitting equivalent length 5 feet. Section C equivalent length is 5 feet because it has one straight fitting equivalent length 5 feet. Section D equivalent length is 50 feet because it is given in the question. Now that we have the actual and equivalent length, we can find the effective lengths by adding the actual length to the effective length. Section A effective length is 16 feet because 6 plus 10 equals 16. Section B effective length is 13 feet because 8 plus 5 equals 13. Section C effective length is 17 feet because 12 plus 5 equals 17. Section D effective length is 80 feet because 30 plus 50 equals 80. The total effective length. The total effective length equals the measured length from the farthest supply outlet through the equipment into the farthest return outlet, plus the equivalent lengths of all turns and fittings. Add all the effective lengths together to get the total effective length. 16 plus 13 plus 17 plus 80 equals 126 feet. Degree days. Degree days are the difference between the daily average temperature, high temperature plus low temperature divided by 2 in 65 degrees Fahrenheit. Degree days calculations assume that when the outside temperature is 65 degrees Fahrenheit, heating/cooling is not needed to be comfortable. Degree days are used mostly for tracking energy use between two periods of time. Degree days are the number of degrees by which the average daily temperature is higher than 65 degrees Fahrenheit or lower than 65 degrees Fahrenheit. The two types of degree days we will focus on are heating degree days, HDD, cooling degree days, CDD. Heating degree days, HDD, are used when the average temperature is above 65 degrees Fahrenheit. Cooling degree days, CDD, are used when the average temperature is below 65 degrees Fahrenheit. If the average temperature is above 65 degrees Fahrenheit, you subtract 65 from the average temperature to find the degree cooling days. If the average temperature is below 65 degrees Fahrenheit, you subtract the average temperature from 65 to find the degree heating days. Let's work through a few example questions. If the highest temperature for a particular day was 85 degrees Fahrenheit and the lowest temperature was 60 degrees Fahrenheit, what is the degree day? 85 plus 60 divided by 2 equals 72.5 degrees Fahrenheit. Since this is above 65 degrees Fahrenheit, you subtract 65 to find the cooling degree days. 72.5 minus 65 equals 7.5 cooling degree days. If the highest temperature for a particular day was 40 degrees Fahrenheit and the lowest temperature was 19 degrees Fahrenheit, what is the degree day? 40 plus 19 divided by 2 equals 29.5 degrees Fahrenheit. Since this is below 65 degrees Fahrenheit, you subtract 29.5 from 65 to find the heating degree days. 65 minus 29.5 equals 35.5 heating degree days. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Interior Design Temperatures Code Requirements. The International Residential Code, Section R302.1, Interior Design Conditions, says the interior design temperatures used for heating and cooling load calculations shall be a maximum of 72 degrees Fahrenheit for heating and minimum of 75 degrees Fahrenheit for cooling. We will be using these indoor design temperatures for load calculations. 70 degrees Fahrenheit for heating in the winter, 75 degrees Fahrenheit for cooling in the summer. The basic formula for heat transfer is an important formula to have memorized for load calculations. The basic heat transfer formula is BTUH equals area times U value times temperature difference. Note that areas must be given in square feet. Also note that temperature difference is the inside temperature minus the outside temperature. You will use this formula for heat loss through walls, windows, doors, ceilings, floors, etc. This formula is for conditions other than standard air only. Let's practice an example. The temperature on one side of the 4-inch thick 4x4 foot R19 fiberglass insulation bat is 20 degrees Fahrenheit. If the other side it is 70 degrees Fahrenheit, what is the bat's heat transfer rate? Step 1. Convert R value to U value. U value is 1/19, which equals 0.0526. Step 2. Find the area. The area dimension is 4 feet by 4 feet, so the area is 16 square feet. Step 3. Find the temperature difference. 70 degrees minus 20 degrees makes the temperature difference 50 degrees. Step 4. Use the basic heat transfer formula. A times U times TD equals 16 times 0.0526 times 50 equals 42.07 BTUs per hour. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Specific heat. Specific heat is the amount of heat necessary to raise the temperature of 1 pound of a substance 1 degree Fahrenheit. Every substance has a different specific heat. Air has a 0.24 specific heat, water's is 1, ice has 0.5 specific heat, and lead has a specific heat of 0.16. Sensible heat. Sensible heat is heat you can feel and measure with a thermometer. The formula for sensible heat is sensible BTUs equals pounds times specific heat times temperature difference. Let's practice an example. Water has a specific heat of 1. What is the amount of sensible heat, BTUs, required to heat 3 pounds of water 15 degrees Fahrenheit? Use the sensible heat BTU formula. BTU equals pounds times specific heat times TD. BTU equals 3 pounds times 1 specific heat times 15 TD equals 45 BTUs. Lead has a specific heat of 0.16. What is the amount of sensible heat required to heat 3 pounds of lead from 60 degrees Fahrenheit to 75 degrees Fahrenheit? Answer: BTU equals 3 pounds times 0.16 times 15 equals 7.2 BTU. Note that over 6 times more BTU is required to raise the temperature of water compared to lead. Let's work through another example. Click the next button or on each tab to see how sensible heating BTU is measured by the formula BTUH equals 1.1 times CFM times TD. This sensible heat formula is one of the most important formulas in the HVAC industry. Memorize it. 1.08, frequently rounded to 1.1, is the basic industry standard based on the air density under standard conditions. 70 degrees Fahrenheit at sea level at 50% relative humidity. It is important to understand that the 1.1 multiplier is not simply a constant that you can use with every HVAC calculation. It is the most used one, so we will be using it for all sensible heat calculations. So where does the 1.1 multiplier come from? It takes 0.24 BTU of heat, specific heat of air, to change the temperature of 1 pound of air by 1 degree Fahrenheit. 1 cubic foot holds 0.075 pounds feet to the third density of air at standard day conditions. This is where the 1.1 comes from. 0.24 BTU times 0.075 pounds feet to the third times 60 minutes per hour equals 1.08. After rounding up, 1.1 is the number of BTUs required to heat 1 foot to the third of air 1 degree. Let's work through a simple heat loss question. Volume equals 4,200 feet to the third. TD equals 52. ACH equals 0.35. Wall air infiltration is 11 CFM. What is the heat loss due to infiltration? First, convert ACH to CFM. CFM equals volume times ACH times 0.0167. CFM equals 4,200 times 0.35 times 0.0167 equals 24. Then add the wall CFM. 24 plus 11 equals 35 CFM. Next, use the sensible heating BTU formula. BTUH equals 1.1 times CFM times temperature difference. 1.1 times 35 times 52 equals 2002 BTU. Latent heat is hidden energy supplied or extracted to change the state of a substance without causing a change in its temperature. You can think of latent heat as hidden heat. A simple formula to find latent BTU is total BTU minus sensible BTU. Total heat, or enthalpy, is the internal energy and the product of its pressure and volume. BTUH equals 4.5 times CFM times delta H is the formula for total heat gain. The total heat content of air combines both sensible and latent heat. 4.5 comes from 60 minutes times 0.075 cubic feet density of air. Delta H is the change in enthalpy between return and supply. Try this example. The answer will be shown next. On a 4-ton cooling unit, the fan table shows that the fan is delivering air at 1,300 cubic feet per minute. The enthalpy change through the cooling system is 5.4 BTUs per pound of air. What is the equipment BTUs? Answer: 31,590 total BTUs. Ohm's law states that electric current is proportional to voltage and inversely proportional to resistance. The diagram is a simplified illustration to show the algebraic equivalent of 3 possible equations. Volts to watts. 3.41 BTUH equals 1 watt. Also, there are 1,000 watts in 1 kilowatt. What is the voltage of 10-watt power with a current of 2 amps? Volts equals watts divided by amps. 10 divided by 2 equals 5 volts. Watts to amps. The formula to convert watts to amperes is amperes times volts. For example, what is the wattage of a 2-amp current and a voltage of 5 volts? 2 times 5 equals 10 watts. Volts to amps. The formula to convert volts to amps is watts divided by volts. How many amps do you need if you have a 10-watt power running at 5 volts? 10 divided by 5 equals 2 amperes. Amps to watts. The formula to convert amps to watts is amps times volts. How many watts power a current of 2 amps and a voltage of 5 volts? 2 times 5 equals 10 watts. Watts and BTUH. 1 watt equals 3.41 BTUH. 1 kilowatt equals 1,000 watts. Watts equals BTUH divided by 3.4. What is the heat gain from 2 40-watt light bulbs? First, multiply the wattage by the number of lights. 2 times 40 equals 80 watts. Next, multiply the wattage by 3.4 BTUH. 80 times 3.4 equals 272 BTUH. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. How many watts are required for 43,000 BTUH? 43,000 divided by 3.4 equals 12,647 watts. How many kilowatts are required for 43,000 BTUH? Answer: 12,647 divided by 1,000 equals 12.647 kilowatts. Let's work through another example. Click the next button, amperes. Amperes equals watts divided by volts. Note, there are 1,000 watts in 1 kilowatt. How many amps are required for a 3.5 kilowatt unit supplied by 240 volt wiring? First, convert kilowatts to watts. 3.5 kilowatts times 1000 equals 3,500 watts. Then divide watts by volts. 3,500 divided by 240 equals 14.58 amps. Let's keep practicing. You need 120,000 BTU-H for a cooling system. How many amps are needed when using a 240-volt electrical wiring? First, convert BTU-H to watts. 120,000 BTU-H divided by 3.4 equals 35,294 watts. Next, convert watts to amps. 35,294 divided by 240 equals 147 amps. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Power equals voltage times current. Amps equals volt amperes divided by volts. VA stands for volt ampere. Volt ampere is a unit of electrical power equal to the product of 1 volt and 1 ampere and equivalent to 1 watt of direct current. A single-phase electrical circuit with 1800 volt amperes of power at 240 volts. What is the circuit current rating in amps? Answer: 1800 divided by 240 equals 7.5 amps. Let's work through another example. Click the next button or on each tab to see how to solve and the correct answer. Calculating air conditioning loads. When sizing overcurrent protection, branch circuit, feeder, and service conductors for air conditioning equipment, most air conditioning condensing units are sized according to tons, not horsepower. For air conditioning, this program will use the following information. A practical approach is to convert the AC equipment from tons to VA. 1 ton of air conditioning condensing load equals 2,400 VA. To find the load in amperes, simply apply Ohm's law current formula. I equals P divided by E. Multiply by 2,400 volt amperes times the tonnage of the AC unit, which will give VA, and divide the VA by the voltage. A 240-volt single-phase 4-ton AC condensing unit is to be installed. In amperes, this condensing unit will draw blank of current. A. 40 amperes. B. 35 amperes. C. 45 amperes. D. 50 amperes. Solution. I equals 4 times 2,400 volt amps divided by 240 volts equals 9,600 volt amps divided by 240 equals 40 amperes. Let's practice calculating operating costs. A 16-SEER 3-ton air conditioner rating is approximately 18 amps powered on a 240-volt circuit. What is the wattage consumed? 18 times 240 equals 4,320 watts, which is 4.32 kilowatt hours. If 1 kilowatt hour costs 12 cents, how much does it cost to run the air conditioner for 1 hour? 0.12 times 4.32 equals 0.5184. The costs to run the air conditioner for an hour is 52 cents. Let's work through another example. Click the next button or on each tab to energy efficiency terms. AFUE means annual fuel utilization efficiency. This is expressed as a percentage. The minimum AFUE for new furnaces is 78%. SEER means seasonal energy efficiency ratio. It is the average number of BTUs an air conditioner will produce for each watt. A good SEER rating is typically 14 or higher. An air conditioner with a SEER of 14 will produce 14 BTUs per watt input. HSPF means heating season performance factor. BTU divided by watt hours. For example, a heat pump with a 20 HSPF rating outputs 20 BTU of heat energy per watt hour of electricity consumed. Dry bulb temperature. The dry bulb temperature measures the ambient air temperature with a thermometer. Dry bulb temperatures are not affected by the moisture of the air. The heating design temperature is the outdoor dry bulb temperature that is exceeded during at least 99% of the hours of the year. Wet bulb temperature measures how much water vapor the air can hold at current weather conditions. Temperature indicated by a moistened thermometer bulb exposed to the airflow. Lower wet bulb temperature equals drier air. Dry bulb and wet bulb temperature. Wet bulb depression. The difference between the dry bulb temperature and wet bulb temperature is called wet bulb depression. At 100% humidity, dry bulb and wet bulb temperatures are identical. The wet bulb depression is 0 in these conditions. The study of air, specifically its properties and behavior, is known as psychrometrics. Dry air weighs approximately 0.075 pounds per feet to the third at standard atmospheric pressure. The weight of air in a room can be calculated by multiplying the room's volume by the weight of the air. Example: how much does air in a 12-foot by 12-foot by 8-foot room weigh? Calculate the volume of the room and multiply the volume by the weight of dry air. 12 times 12 times 8 times 0.075 equals 86 pounds. Let's work through another example. Click the next button or on each tab to psychrometric charts contain air data. Dry bulb temperature, wet bulb temperature, relative humidity, specific volume, moisture content, heat content, dew point temperature. This is a generalized psychrometric comfort chart for summer. Dry bulb at the bottom of the chart is regular dry air temperature. Specific humidity, amount of moisture in the air, is listed on the vertical axis on the right. Specific humidify is measured in grain units. Wet bulb, dew point, or saturation temperature. The top curved line starting at the bottom left and moving up to the top right is the 100% saturation line. At 100% saturation, air cannot hold any more water. It is also called dew point or wet bulb. Relative humidity. The curved lines represent relative humidity. Enthalpy is the total heat, the combination of sensible heat, horizontal axis, and latent heat, vertical axis. Comfort zone. The red box in the middle shows the comfort zone. The comfort zone is not always included on these charts. What is the relative humidity at 72 degrees Fahrenheit at 60 GR of moisture? Answer: 50%. What is the dew point temperature if air has 60 GR of moisture? Answer: 53 degrees Fahrenheit. What is the wet bulb temperature at 70 degrees Fahrenheit at 60 GR of moisture? Answer: 60 degrees Fahrenheit. Let's say we have a temperature reading of 75 degrees Fahrenheit, dry bulb, and 60 degrees Fahrenheit, wet bulb. What is the relative humidity? Answer: approximately 40%. HVAC symbols. The following are common HVAC blueprint schematic symbols. In order to read wiring diagrams and schematics, you need to know what the symbols mean. These are common symbols. Manufacturers use different labels, but these symbols will always be the same. The symbol for supply air is a box with two diagonal lines. The symbol for return air is a box with one diagonal line. The symbol for thermostat is a T inside of a circle. This is the fitting symbol drawing for a boot. Boot fitting from branch to stack. An air register has the capability of adjusting the airflow by opening and closing a damper or flaps. Registers cover a hole in the wall, floor, or ceiling where the air duct enters the room. A combination of stack boots and heads makes up the basic structure of a ductwork. Stack boot is the professional term for vertical duct, which, as the name suggests, helps airflow vertically. Boots deliver conditioned air into living space and houses the register. Valve. Gate valve, globe valves, and solenoid valves are variations of this basic valve symbol. Switch symbols are employed to represent many common control sensing devices. This is the symbol for a normally open contact, which is abbreviated to NO. These are for relay, compressor contactors, or motor contactors. When you see a normally open contact, this is the condition it is in with no power supplied. The HVAC system is not operating. Please note that wiring diagrams always show the unit with the power off. Unless the instructions located on the diagram say differently, every standard wiring diagram should be drawn in the neutral condition. Normally closed contact symbols have a line through them. When an HVAC system is energized, the normally closed contact will open. This is the symbol for a single-pole, single-throw switch. An on-off switch allows electrical current to flow only when it is in the closed, on position. This is the symbol for a single-pole double throw, also known as a two-way switch. A two-way changeover switch directs the flow of current to one of two routes according to its position. Some SPDT switches have a central off position and are described as on-off-on. Pressure switch normally open. Normally open switches are drawn with the movable contact below and not touching the stationary contact. Normally closed switches, on the other hand, are drawn with the movable contact above and touching the stationary contact. Thermostat control switches and contacts. This symbol is a temperature switch normally closed. This is similar to the pressure control switch. The symbol shown is normally closed, so it opens on temperature rise. The zigzag indicates a temperature-activated switch. Push buttons contain both movable and stationary contacts. The normally open push button shows the movable contact above and not touching the stationary contacts. The normally closed push button symbol shows the movable contact touching the stationary contacts. A complete circuit exists and current can flow from one stationary contact to the other. When pressure is applied to the button, the movable contact will move away from the two stationary contacts and open the circuit. Wires connected. Connected wires are depicted by a dot on the back lines that represent wires. Sometimes it'll be a circle instead of a black dot. Wires not connected. Wires not connected do not have a dot. Ground. A connection to earth. For many electronic circuits, this is the 0 volts of the power supply, but for mains electricity and some radio circuits, it really means the earth.